Imagine for a moment, you're nestled in the passenger seat of an autonomous vehicle, maybe hurtling down the highway at 70 miles an hour.
Hmm.
Or perhaps you're an airline pilot, relying on an autopilot system to guide a massive aircraft through complex airspace. What's the invisible force making all of this possible, and maybe more importantly, making it profoundly, unimpeachably safe?
Right.
It's software. Intricate, meticulously crafted lines of code that dictate everything from emergency braking to precision flight paths. But here's the fundamental question, I think, that underlies all this incredible technology. How do we, as a society, ensure that this software isn't just functional, not just clever, but truly safe and reliable, especially when human lives are literally on the line?
Yeah, that's the core challenge.
Today, we're jumping into a deep dive into the fascinating yet often unseen world of functional safety. Specifically, we're going to unpack a pretty groundbreaking project, a process for Spark software to meet ISO 26262. Our unique source material for this exploration comes directly from a publicly available GitHub repository, aptly named Spark process, originating from none other than NVIDIA.
Ah, interesting. NVIDIA's own process, publicly available.
Exactly. So our mission in this deep dive is clear. We want to unravel the complexities of this remarkable project, understand its profound significance in the realm of safety-critical software, and highlight the truly innovative approaches being used by industry leaders like NVIDIA and Adacor to achieve, really rigorous safety compliance.
Right.
This isn't just about technical specifications, it's about the very foundations of trust in our increasingly software-driven world. So let's unpack this.
It's an incredibly important area, definitely, because as you've highlighted, so much of our modern infrastructure, from our personal vehicles to sprawling energy grids, even medical devices, relies on software that must simply not fail.
Right. Can't fail.
And if it does, the consequences aren't just inconvenient, they can be catastrophic, leading to serious injury or even loss of life. So this deep dive into a specific tangible example like NVIDIA's Spark process really helps illustrate in concrete terms how leading companies are tackling this immense challenge head-on, building safety right into the core of their systems.
That makes perfect sense. And when we talk about safety in the context of vehicles, there's one international standard that immediately springs to mind, almost like a foundational text for automotive safety, ISO 26262.
The big one.
Yeah. But what's the true scope of this standard? Is it just about preventing coding errors, or is it something far more holistic?
That's a crucial distinction. At its core, ISO 26262 is an international standard specifically designed for the functional safety of electrical and/or electronic systems found in road vehicles. It's not just a guideline or a set of best practices, it's a comprehensive, systematic framework.
Systematic, okay.
The why behind it is to prevent what the standard terms unreasonable risk due to malfunctions. Think about that phrase, unreasonable risk.
Yeah.
It acknowledges a fundamental truth. In complex systems, achieving absolute zero risk is often, practically impossible.
Right, you can't eliminate everything.
Exactly. But what ISO 26262 demands is that any residual risk is systematically identified, analyzed, and brought down to an acceptable, tolerable level, a level that is deemed safe for human interaction and the broader environment.
So we're not just talking about preventing a single line of code from crashing an app like on your phone. We're talking about a complete philosophical shift towards anticipating potential failures and building in safeguards from the very, very beginning.
Precisely. This standard provides a meticulous, systematic approach to managing and mitigating potential hazards throughout the entire product lifecycle.
The whole thing.
The whole thing. Imagine it like a grand architectural blueprint, not just for a single building, but for an entire city designed for safety. This blueprint ensures that every single component, every decision, and especially every line of code in a car's critical systems, from the anti-lock brakes to the steering assist, the airbags, or the sophisticated sensor fusion in an autonomous car, is designed under this umbrella to prevent harm.
Wow.
It starts right from the initial concept phase, even before a single line of code is written. You're defining potential hazards, assessing their risk, and setting safety goals.
Okay.
Then, throughout product development, it dictates how hardware and software should be designed, tested, and verified to meet those goals. This includes detailed requirements for documentation, change management, configuration control, and robust fault handling.
So traceability is key.
Absolutely key. It extends to production, ensuring that safety-critical components are manufactured correctly, and then into operation, service, and even eventual decommissioning. It's about building safety in from the ground up, verifying it at every step, and maintaining it throughout the vehicle's lifespan. This comprehensive approach means looking at fault tolerance, diagnostic coverage, and systematic error avoidance, ensuring that safety is not an afterthought, but an inherent quality.
And when you, our listener, are driving your car or maybe riding in a cutting-edge autonomous vehicle someday soon, your safety and the safety of your loved ones on the road implicitly relies on adherence to these kinds of rigorous global standards.
Hmm.
It's the silent guardian in the background, ensuring that the technology you interact with every day has been built with an unwavering commitment to your well-being. It's the assurance that decades of engineering knowledge and safety analysis have been poured into the systems guiding your journey, allowing for rapid innovation without sacrificing safety.
Absolutely. And the standard even defines different automotive safety integrity levels, or ASILs, from A to D.
ASILs, right, I've heard that term.
Yeah. ASIL A, for example, might apply to a component where a malfunction could lead to minor injuries, perhaps just a slight inconvenience. But ASIL D is the most stringent level, reserved for components whose failure could lead to severe or life-threatening injuries, or even fatalities.
Like brakes or steering.
Exactly. Think of an autonomous braking system, or steer-by-wire. The rigor of development, testing, and verification increases dramatically from ASIL A to ASIL D. The Spark process we're looking at is designed to meet these highest levels of integrity, ASIL D, which is why it's so significant.
That makes a lot of sense. Speaking of technology, the NVIDIA project specifically calls out Ada Spark software. Now, for many of our listeners, those might not be the household programming language names like, say, Python or JavaScript.
Probably not, no.
Why would they choose these particular languages for something so critical, especially when developing something as cutting-edge as autonomous vehicle systems?
That's an excellent point, and it gets right to the heart of what makes this project so compelling. Ada is a programming language with an extensive and crucially proven history in some of the most safety-critical domains imaginable. We're talking aerospace, defense systems, nuclear power plants, air traffic control, railway signaling.
So high-stakes stuff. What does that mean exactly? Strong typing.
It means the compiler rigorously checks that data types are used correctly. So you can't accidentally treat, say, a speed value as if it were a temperature value. This catches many errors at compile time that other languages might only expose at runtime, often in unpredictable and potentially dangerous ways.
Ah, okay. So errors caught early.
Exactly. They also have robust error handling mechanisms, promoting graceful degradation or safe shutdown instead of just catastrophic crashes. Modularity is built into their DNA, making complex systems easier to manage, verify piece by piece, and understand.
Makes sense.
But the true game changer, especially for Spark, is its deep support for formal methods.
Formal methods. That sounds formal.
It is. Think of it not just as rigorous testing, but like a mathematician proving a theorem. With formal methods, you use mathematical techniques and tools to prove that certain properties of your software are true, universally, regardless of how many times you run it or what specific inputs it receives. Instead of just testing to find bugs, which is kind of like looking for needles in a haystack, you are mathematically demonstrating the absence of certain types of bugs, like runtime errors, or proving that the code will always behave in a specified safe way under all defined conditions.
That's a huge distinction then. It's not just, we tested it extensively and it seems fine, but we've mathematically proven it operates correctly under these conditions, covering every possible scenario. How does that compare to common languages like C or C++, often used in embedded systems?
Exactly. This drastically reduces the likelihood of subtle, dangerous bugs that might escape even the most comprehensive traditional testing regimes. This ability to formally verify code is a cornerstone of meeting ISO 26262's highest safety integrity levels, like ASIL D, which demands the absolute highest assurance. Common programming languages like C or C++F, while powerful and flexible, weren't really designed with the same rigorous safety and verifiability requirements as Ada and Spark.
Right, they have other strengths.
They do, but they also allow for much more implicit behavior, more ways to make subtle errors like buffer overflows or using uninitialized variables, things that have plagued C++ development for decades. They simply don't lend themselves as easily to formal proof without adding significant, complex external tooling and highly disciplined, often very labor-intensive processes.
So it's harder to bolt on safety later?
Much harder and less reliable. This raises an important question, I think. In a world craving reliability, especially as software permeates every aspect of our lives, from medical devices to smart grids, why don't more critical systems leverage languages with this level of inherent verifiability? The inherent design philosophies of Ada and Spark align perfectly with the demands of safety certification, providing a powerful assurance that is often lacking in other development environments. It's about building safety in from the ground up, making correctness the default rather than trying to bolt it on later through extensive and ultimately never exhaustive testing.
With such powerful tools and a clear need for safety, the next logical question is, who championed this groundbreaking approach and how did they build this process? It wasn't developed in isolation, was it? Surely not.
Not at all. The initial version of this reference process, as they call it, was actually joint development between two major players, NVIDIA and Adcore.
Okay, NVIDIA and Adcore.
And crucially, it then underwent independent review by TÜV.
TÜV, right, the certification body. That's a formidable lineup right there.
What distinct expertise does each of these entities bring to the table in a collaboration like this, especially for something as high stakes as automotive functional safety? Well, think of it as a powerhouse alliance. The technological innovator, the language specialist, and the impartial safety arbiter, all converging to forge a robust safety standard. NVIDIA brings its immense deep expertise in high-performance computing, particularly its prowess in AI, deep learning, and developing cutting-edge automotive platforms. They understand the complex interplay between advanced hardware and the sophisticated software ecosystems that run on it, which is absolutely central to autonomous driving.
Yeah, they're at the forefront of that.
Definitely. Adcore, on the other hand, contributes its highly specialized, decades-long knowledge in Ada and Spark for safety-critical systems. They are the experts in extracting the maximum verifiability and reliability from these languages, providing the compilers, tools, and expertise necessary to develop certifiably safe code. Their understanding of formal methods and rigorous development life cycles is pretty much unparalleled.
So the language gurus.
Essentially, yes. And then you have TÜV. They are a renowned international certification body, a third-party expert in safety. Their role here is to provide independent validation and review. They are the impartial arbiter of safety, scrutinizing the entire process to ensure that it meets the highest standards and is truly compliant with ISO 26262. This isn't just a rubber stamp, it's a deep expert audit.
Okay.
So this partnership pools incredibly diverse yet essential expertise to address what is a profoundly complex challenge, ensuring that advanced AI-driven software in vehicles is demonstrably certifiably safe.
So it's not just a theoretical exercise or an internal document. It's a practical, implementable process that has been scrutinized by one of the most respected external safety authorities in the world. This multi-stakeholder involvement isn't just for show, is it?
Precisely. It underscores the sheer seriousness and inherent complexity of achieving functional safety certification in a domain as critical as automotive. It demonstrates a commitment to excellence and a recognition that true safety validation requires multiple independent layers of expertise and rigorous oversight. It also implies a shared commitment to elevating the state-of-the-art across the industry.
Oh, so?
Well, NVIDIA, by collaborating with Adcore and then involving TÜV, is not just building safer products for themselves, but is also contributing to a broader understanding of how such safety can be achieved. This kind of collaboration is crucial for building trust in emerging technologies like autonomous driving.
Now, the GitHub repository itself includes an important disclaimer stating that this is a reference process, not necessarily their current internal development process, and it doesn't guarantee TÜV acceptance or endorsement for specific products built with it. It also mentions that adjustments might be made over time without systematic review from all initial authors. What does it mean for something to be a reference process in this context, and why is that disclaimer so important for us as listeners to understand?
Yeah, that's a really key point. What's fascinating here is that they're sharing a living, evolving document, acknowledging that safety standards and the technological state-of-the-art are always moving targets.
Right, things change fast.
They do. A reference process means it's a foundational, publicly available blueprint, a highly detailed, expert-backed guide to how one might achieve ISO 26262 compliance using Ada and Spark. It's designed to be a robust starting point, a comprehensive example for other organizations or even internal teams within NVIDIA and Adcore when they're developing their own specific products.
So a template, almost.
Kind of, yeah. A very detailed template. The disclaimer is crucial because internal development and certification processes within these companies are constantly evolving. They are likely more dynamic, probably proprietary, and tailored to very specific product lines and their unique requirements. This public version is a formalized, distilled methodology, not a real-time snapshot of every internal tweak or a direct guarantee.
Okay.
And the point about two-seed acceptance means that while two-seed reviewed and provided input on this process, it doesn't automatically mean any specific product built using this process will be certified without its own dedicated product-specific audit by two-seed or another certification body.
Got it. The product still needs its own separate check.
Exactly. It's a critical distinction for legal and compliance reasons,
Right.
emphasizing that the ultimate responsibility for product safety lies with the product developer, not just the process they followed.
So it's a highly authoritative guide, a template for best practices, rather than a rigid rulebook that promises immediate certification for anything built with it.
Absolutely. And it fosters transparency, which is incredibly valuable in a high-stakes field like this. There's also a clear strategic implication to sharing a reference process like this.
What kind of implication?
It allows for broader community input, potentially inviting suggestions and contributions, fostering an ecosystem of shared learning. It helps educate the wider engineering community about best practices in functional safety with Ada Spark, elevating the discussion and practice across the industry. It establishes a common baseline and a shared language for future advancements in functional safety. It's a commitment to transparency and industry improvement within a highly regulated field, showing a path forward without prescribing a static, one-size-fits-all solution.
That transparency actually extends to how this project is maintained, doesn't it? They encourage contributions through issues and pull requests on GitHub, while also being clear about retaining editorial control. It's an interesting blend of open source philosophy and, well, practical necessity.
Yes, that's what truly makes it a living document, in a very real sense. They explicitly state, "We intend to maintain this document through issues and pull requests. Suggestions and contributions are welcome and encouraged," which is very open source-like.
But then there's a catch.
But please note that we can't incorporate modifications that deviate from our needs. And they even go a step further, encouraging anyone whose project has specific goals that diverge from NVIDIA's to create their own fork of the repository, basically their own copy, to modify freely and even invite them to let NVIDIA know about it so they might link to it.
That's a fascinating model. It's open, but clearly controlled. How do they balance those two seemingly opposite ideas, especially when functional safety is at stake? You don't want just anyone merging changes into a safety process.
No, you definitely don't. It's a highly pragmatic and, I think, intelligent approach for high-stakes specialized projects. On one hand, they leverage the incredible benefits of open-source collaboration. Things like community input, transparent peer review from a global community, and the potential for a wider range of perspectives to identify edge cases or improvements.
Getting more eyes on it.
Exactly. On the other hand, NVIDIA retains critical editorial control. This is absolutely essential to ensure the process remains aligned with its strategic objectives and, crucially, its rigorous internal product development needs for automotive safety.
Makes sense.
You can imagine that an open-source contribution that might be theoretically interesting or academically sound, but doesn't fit within their strict ISO 26262 compliance goals for their own products, wouldn't be integrated directly. They simply can't compromise on certifiability. You could compare it to a specialized academic journal in a very precise field. Submissions are absolutely encouraged, and external experts contribute valuable insights. But ultimately, there's a rigorous peer review process and strong editorial oversight that ensures adherence to very specific standards, methodologies, and aims.
Yeah, the editor has the final say.
Precisely. For something as critical as functional safety, you simply can't incorporate every suggestion without careful vetting. There has to be a guiding hand to maintain integrity, consistency, and compliance with the incredibly demanding safety standards. This model demonstrates how critical industry projects can still harness the power of open source to improve and iterate on complex documentation and processes without compromising their core mission of ensuring safety.
And speaking of practicalities, for anyone looking to engage with this, they've laid out the technical foundation for building the document itself. What does it take to actually generate this process document locally, and what does that reveal about its nature?
Right. If you want to build the human-readable HTML or PDF version of the document locally, you need a few common developer tools. Primarily, Python 3, specifically version 3.MIC-0 or newer, is required.
Okay, Python. Pretty standard.
Yeah. You also need GNU-Make, which is a widely used build automation tool, very common in software development, especially on Linux or Mac OS.
Make files. Got it.
And for generating the PDF version specifically, you'll need a comprehensive LaTeX distribution, like TextLive Full. LaTeX is a powerful document preparation system often used for technical and scientific documents, known for its high-quality typesetting.
Right, for complex layouts and math.
Exactly. The actual commands for building it are quite straightforward once you have these tools installed. It involves running a Python command using pip to install the required Python libraries from a requirements.txt file, and then a simple make HTML or make PDF command to compile the document.
What do these technical requirements reveal about the nature of the process documentation itself? It sounds like it's more than just a simple text file someone typed up.
Oh, it absolutely is. The reliance on Python strongly suggests that scripting and automation are central to the process's generation. This isn't just a static Word document or a collection of PDFs that someone manually updates. It's dynamically generated content.
How so?
Python is likely used for processing underlying data. We'll get to TRLC later, which is key here. Generating content sections, checking for consistency, maybe inserting code examples, and ensuring uniformity across various parts of the process document. The use of GNU Make indicates a robust, build system-driven approach to compiling the documentation, much like you would compile software.
Like a software build for a document?
Pretty much. This ensures consistency, reproducibility, and prevents errors that could easily be introduced by manual assembly or copy-pasting, which is critical for a safety-focused document. The ability for anyone to build it locally also empowers contributors and users to thoroughly examine, understand, and even verify the process documentation themselves, enhancing transparency and trust.
That's quite neat.
Yeah, and if you look at the repository's language breakdown on GitHub, it reinforces this programmatic nature. It's like 95.8% Python, 3.7% Makefile, and just a tiny 0.5% CSS for styling the HTML output.
Wow, almost entirely code.
Exactly. This is not a prose document written in a simple text editor. It's a highly programmatic piece of documentation designed for consistency, automated generation, and rigorous control, all key principles when you're aiming for something like ISO 26262 compliance. It's a testament to the idea that even documentation in critical fields can benefit immensely from software engineering principles.
Okay, so it's a living, programmable document. And diving deeper into that structure, you mentioned it's meticulously organized. We're talking about dedicated folders for everything from syntax highlighting to core process documents and detailed tracing information. It sounds like an incredibly complex yet perfectly ordered library.
Absolutely. The repository source organization is a clear indicator of a well-thought-out, modular approach to managing what is undoubtedly a vast and complex document set. You have distinct directories for specific components. Pigments for custom Spark syntax, highlighting little details like that, are crucial for readability when dealing with code examples within the documentation.
Makes sense.
Just houses the various Python document generation scripts we just discussed. The main document tree starts at sourceprocessindex.rest, which acts as the entry point using restructured text format. And within that, the actual core process document resides in its own dedicated folder, source process process.
Okay, pretty logical.
But what's truly telling about the depth and rigor of this project are the specialized tracing folders. There's source process checklist, which contains files used to generate compliance checklists. Think of step-by-step guides derived from the process. Then, source process tracing Spark assumptions for tracing assumptions made during Spark development, which is absolutely vital for formal verification.
Tracking assumptions, why is that so important?
Because formal proof often relies on certain preconditions or assumptions about the environment or inputs. You need to rigorously document and track these assumptions to ensure the proof holds true in the real system.
Ah, okay.
Got it. And finally, source process tracing ISO 26262, which contains all the direct ISO 26262 tracing information, linking specific requirements from the standard itself to parts of the process defined in the document. This shows how the process meets each relevant clause of the standard.
So direct mapping to the ISO standard, what are the benefits of this kind of granular modular organization for such an incredibly complex document, especially when safety and compliance are paramount?
Well, imagine that meticulously organized library we talked about, where each section, from the main process to the detailed checklists and tracing documents, has its own dedicated accessible shelf. For a document set this vast and complex, modularity is absolutely paramount. It ensures maintainability.
Easier to update.
Much easier. If you need to update a specific checklist related to, say, a new compiler feature or a refinement in a verification technique, you know exactly where to go without inadvertently affecting other unrelated parts of the document. This minimizes the risk of introducing errors during updates.
Right. Less chance of breaking something else.
Exactly. It also enhances scalability. allowing the process to grow and adapt over time as technology evolves or new safety considerations emerge, without becoming unwieldy or unmanageable. Each component serves a specific, well-defined purpose, contributing to the overall integrity, traceability, and comprehensiveness of the entire process. This kind of structured organization is absolutely essential when you're trying to meet the rigorous auditing and traceability requirements of a standard, like ISO 26262, where every requirement, every decision must be traceable and verifiable. It's really an engineering approach to documentation itself.
And embedded within this modular structure is something you hinted at earlier, something that sounds like a real game changer, perhaps even a revolutionary concept. TRLC files. This is where it gets really interesting.
It truly is. This is, I think, one of the most innovative aspects. A large part of this process document isn't just manually written text. It's dynamically generated from TRLC files. TRLC is described as a language and tool for expressing requirements with attached metadata and policy. Now, unfortunately, the source doesn't spell out the acronym TRLC, but its function is what truly matters here.
Okay, so requirements plus metadata plus policy, all defined in a special language. That sounds incredibly powerful for ensuring consistency, not just in documentation, but potentially in the actual compliance process itself.
It truly is, and this represents a significant paradigm shift. This is a prime example of what people are increasingly calling requirements as code or policy as code. Instead of requirements being static paragraphs sitting passively in a document, they become living, executable entities, or at least machine-readable data structures.
Executable requirements, how does that work?
Well, maybe not directly executable in the traditional sense, but machine parsable and actionable. By defining requirements, their associated metadata, like their source, their priority, their ASIL level, who's responsible, verification method, and the policies governing them in a structured, machine-readable format like TRLC, the process gains immense advantages.
Okay, like what?
First, it allows for automated input validation. The system, maybe those Python scripts, can automatically check for consistency and correctness of requirements. Are there contradictory statements? Are there requirements without owners or verification plans? Are all high-level requirements decomposed properly? No more manually scanning thousands of lines of text to find these issues. Imagine the manual effort saved and the potential for human error eliminated right there.
Huge time saver and safer.
Definitely. Second, it enables automated generation. The Python scripts we discussed earlier can read these large data sets of TRLC and generate the .rceased restructured text, files those structured text documents that form the basis of the final HTML or PDF. This ensures that your human-readable documentation is always directly derived from and perfectly consistent with your formal machine-readable requirements. This eliminates a huge source of human error where documentation might get out of sync with the actual requirements or the developed code.
The doc always matches the spec.
Pretty much. Third, and perhaps most importantly for functional safety, this data is machine parsable. This means it can feed directly into other tools. Imagine these formalized requirements feeding into automated testing frameworks, perhaps generating test stubs or configurations, or directly into compliance checking tools that can analyze the code or test results to verify whether specific requirements are met, or even into code generation tools that can automatically create scaffolding or specific modules based on these formal requirements. For example, a TRLC requirement might state, the autonomous braking system must initiate braking within 50 milliseconds of detecting an obstacle categorized as imminent collision with ASIL-D integrity. This requirement isn't just text, it's a data point with associated metadata. ASIL-D, timing constraint 50 meters, verification method, simulation and hardware in the loop testing, traceability link, ISO 26260 Part 6 Clause XY. A tool could then potentially automatically generate test cases to verify this timing or even analyze the code control flow to help prove it meets that deadline.
This sounds like it could be revolutionary far beyond just automotive software. If you can define policy as code, you could apply this almost anywhere rules and requirements are critical.
Exactly. This really changes the game. TRLC, or concepts like it, represent a paradigm shift, moving from static documents to policy as code, where regulations and requirements are living, machine-actionable entities. This isn't just about faster checks. It's about fundamentally eliminating entire classes of human error and enabling proactive compliance across industries.
Like where else?
Consider how this could revolutionize sectors like medical devices, where patient safety is absolutely paramount. Defining regulatory requirements for a pacemaker or a surgical robot in a TRLC-like format could allow for automated, continuous compliance checks throughout its development lifecycle and potentially even during operation through logging and analysis.
That would be huge.
Or think about financial services, where regulatory compliance is incredibly complex and stringent. Know your customer rules or anti-money laundering policies could potentially be expressed as TRLC or similar, allowing algorithms to automatically enforce and verify compliance in real-time transactions, potentially reducing fraud and regulatory fines much more effectively. It moves beyond just auditing after the fact to building compliance directly into the system's DNA. This approach minimizes errors, accelerates compliance processes, and fundamentally builds trust in the systems that underpin our most critical industries. It's a powerful concept for any field where consistency, traceability, and verifiable adherence to rules are critical.
Fascinating stuff. And naturally, a project of this scale and collaborative nature involving multiple companies and standards has a complex legal framework underpinning it. It's not just a single license, but layers of them, reflecting the diverse contributions, right?
That's right. The licensing information is quite detailed, and it really reflects the complex intellectual property landscape of a project built on various contributions and existing standards. The core material is under the copyright of both NVIDIA and Adacor, acknowledging their joint development and ownership for the years 2021 to 2025.
Okay, joint copyright.
Then the pigments parser, which is used for the nice syntax highlighting of Spark code within the documentation, is licensed separately. It's actually inherited from the Spark 2014 repository, so you'd have to check that specific license if you were really digging in.
Right.
Crucially, any material quoted directly from the ISO 26262 standard is clearly noted as copyrighted by ISO and reproduced with explicit permission from the American National Standards Institute, ANSI, on behalf of the International Organization for Standardization. All rights for that specific content are reserved to ISO. They're very careful about that attribution.
So they're meticulously citing the standard they're complying with, even down to the copyright level? Makes sense.
Precisely. And then the overarching process document itself, the bulk of the generated text, is licensed under the GFDL v1.3. That's the GNU Free Documentation License, version 1.3.
GFDL. How is that different from other open source licenses?
It's primarily designed for documentation, manuals, textbooks, that kind of thing. It ensures its free distribution and modification, but it also has a strong copyleft clause, meaning any derivative works or modifications must also be licensed under the GFDL. This fosters open collaboration while ensuring that the core process remains freely shareable and adaptable under the same terms.
Okay, so the documentation stays free. What about the code that generates it?
Good question. Any supporting tools and scripts, which would be the Python scripts and makefiles we discussed for generating the document, are licensed under the GPL v3, the GNU General Public License version 3. This license is for software and similarly ensures the openness and freedom of those utilities. Anyone can use, modify, and redistribute them, provided they adhere to the same open source terms, keeping the tool chain open as well.
That's a careful balancing act, isn't it? Balancing open contribution with necessary protections for the original authors and the standards bodies whose work they rely on. It ensures that the project can be widely adopted and modified, but also respects existing intellectual property.
It is. This layered approach showcases a meticulous attention to IP management. It balances the desire for open contribution and industry-wide benefit with necessary protections for the original creators and the strict requirements of intellectual property in such a regulated field. It's a very robust legal groundwork that underpins collaborative, open-source efforts in such critical and sensitive domains. You have to be absolutely clear about what can be used, how it can be modified, and what rights remain with the original creators to ensure widespread adoption and legal clarity.
And behind all these impressive technical and legal structures are, of course, the people. The repository acknowledges a list of key contributors. It's easy to get lost in the tech sometimes, but there are brilliant minds driving this forward.
Indeed. It's absolutely vital to remember that behind every complex technical achievement, especially one of this magnitude and criticality, are dedicated experts. The repository explicitly thanks several individuals, listed in lexicographic order. Brian Gake, Dan Hetna, Dmitry Kulagin, Dwayne McInerney, and Florian Shanda from NVIDIA.
Okay.
Alongside Erwan Leguiu, Vasily Fofanov, and Yannick Moy from Adacor.
Right, the two main collaborating companies.
Exactly. These individuals are really at the forefront of shaping functional safety practices for cutting-edge technologies like autonomous vehicles. Their cross-company collaboration highlights the truly collaborative and interdisciplinary nature of advancing industry standards. especially in areas that demand the highest levels of safety, reliability, and provable correctness.
It takes a team effort.
Definitely. These aren't just developers. They are likely safety engineers, formal method specialists, tool developers, and system architects who understand both the deep intricacies of software and hardware and the profound implications of its failure. Their work directly impacts the reliability and safety of the technology we use every single day, whether we realize it or not. They are literally building the trust into the digital systems that govern more and more of our lives.
And finally, when we look at the repository itself on GitHub, the metrics are quite specific, as you find sometimes with these specialized projects. 17 stars, 1 fork, 3 watchers, as of when we looked. The explicit topics listed are ISO 26262 and Ada Spark. So what does this all mean? These numbers might seem, well, modest compared to some viral open source web frameworks or consumer-facing apps that get thousands of stars.
That's a great observation, and it leads to a crucial insight about the nature of this project. While these numbers might seem modest compared to, say, a popular JavaScript library with millions of downloads, they are incredibly significant for a highly specialized, deeply technical, and compliance-focused repository like this one. Its impact isn't measured in broad popular adoption, but rather in its critical influence on a very niche but vital industry.
So not aiming for quantity here.
Not at all. This isn't a project designed for mass appeal or hobbyists. It's a foundational piece for a very specific, probably quite elite group of engineers, researchers, tool vendors, and companies working on the absolute cutting edge of safety-critical automotive systems and potentially other high-integrity domains that might look to it for inspiration. The presence of ISO 26261, Ada Spark as topics immediately signals its specialized nature to those in the know. It signifies a project that, while perhaps not widely known outside of specific engineering circles, holds immense strategic importance for the future of safety-critical systems, literally shaping how safe software is built and certified globally, especially when using these specific technologies. It's about quality and profound impact within a specific high-stakes domain, rather than sheer quantity of users or stargazers.
What an incredible journey we've taken today through the NVIDIA Spark process. This deep dive has really illuminated, I think, the critical aspects of achieving functional safety in software, a topic that directly impacts our daily lives in ways we might not even consider.
Definitely.
We've gone from the absolute necessity of rigorous international standards like ISO 26262, which forms the very constitution of automotive safety, you could say,
That's a good way to put it.
to the unique power of languages like Ada and Spark, which are literally built for trust and provable correctness, allowing us to mathematically guarantee certain aspects of software behavior in ways other languages just can't easily match.
Right, that formal verification aspect is key.
We explored the groundbreaking innovation of TRLC, which transforms static requirements into living, machine-parsable code, paving the way for unprecedented automation, consistency, and proactive compliance policy as code.
A really powerful concept.
And we've highlighted the collaborative spirit of industry leaders, from NVIDIA to Adacore and the involvement of TwoSud, who are openly sharing their expertise to push the boundaries of what's possible in safe software development.
Like, collaboration is essential.
So, as our world becomes increasingly reliant on complex software embedded in everything from our vehicles to our essential infrastructure, it forces us to consider: how might the principles exemplified in the Spark process, its profound emphasis on provable correctness, its embrace of automated validation through things like TRLC, and its transparent collaborative development philosophy, how might these become the foundational blueprint for trust and reliability in every single aspect of our digital future?
That's the big question, isn't it?
Yeah. Think about how these rigorous standards, born from the high-stakes world of automotive safety, might extend far beyond specific industries to become a universal expectation for all software that truly touches and shapes our lives, from controlling critical medical devices to managing our power grids, or even the algorithms influencing our daily decisions. Could this level of rigor become the norm?